So something to note, I put this as an announcement on Quarkus. I've extended the due date for exercise 1 until 4 p.m. today. I guess it shouldn't have been in the middle of class. That was a weird time to have done it. But if you dash off right now to complete this exercise, I will understand. And with any luck, this lecture will be properly recorded, so you'll be okay. So this is just to collect a whole bunch of people that tried to download the program at like 3 p.m. on Saturday, which was ill-advised. But this is meant to be a learning environment, not a crush your soul environment. So now you get this learning opportunity. Please note that I'm not going to be doing this on the regular. This is not going to be like every exercise you get an extension. This is the one where our job is to work out the technological problems with Logic 2010, right? Okay, any questions about this one? All good with this? Okay, good. Okay. Exercise 2 is now posted, so hopefully we're in the flow of this already. This is due Saturday, January 26th at 4 p.m. It's going to be the time of the week that all of these are going to be due. You can see it's mostly derivations, so these are slightly more advanced derivations. I've not yet taught you how to do these derivations, so if you've tried these on your own and you can't figure them out, that's probably because we haven't learned the skills for them yet. And then some symbolizations, and those symbolizations are going to require the skills that we're going to do on Wednesday when I introduce a couple new connectives. So we will get into all of this week. All of this should be obscure to you now, but by Wednesday will be crystal clear. Any questions about this stuff? Right. Just a quick reminder that you really have to not just submit these things, you have to submit them and check that they've gone through. You have to check the logic, so you're submitting them in Logic 2010, the program. You're checking on the website to make sure that you did not just complete them, but you've submitted them and that the website recognizes that you submitted them, okay? So that's gonna be on, that will be your responsibility going forward, okay? Okay, any questions about course business, that kind of thing? Structure of the course, confusions about what we're doing, where we're going? Okay, great. So today we're really just going to get deeper into derivations. We're going to do a few new skills, but before we do the new skills, I just want to talk about, right off the bat, strategies for doing derivations. And these are going to be general strategies that are going to apply for the rest of the course. These are also strategies that apply to your whole life. So I really enjoy the derivation as life metaphor. So I'll hammer away at it a little bit. But in a derivation, you should always be asking yourself the following two questions. What have I got, and where am I going? These are kind of forward-looking and backward-looking strategies for dealing with the derivation, from getting from premises to conclusion. So what you've got are your assets. Typically, that's going to be some premises. That'll be available lines. Where you're trying to get is, of course, the conclusion. But today we'll deal with sub-derivations, where you might set up a sub-goal for yourself. So I just want to get to the end of this sub-derivation, and how do I get there? So these are forward and backwards looking strategies, and I will come back to this sort of a few times in this lecture, try to illustrate what concretely this means in terms of derivations. But let's just start in first with the first thing, that is, what have I got? So you have the following. You have premises, and once you've derived something, you have that too. With a little caveat that I'll talk about, except the contents of a boxed show line. That's meaningless to you right now. We'll come back to that. But just a little caveat, you've got premises and you've got anything that you've derived on any line as your assets, things that you have to work with. And how do you work with them? What do you do with these things that you have? Well, you use the rules. So the rules that we've presented are how you use your assets, how you turn those assets into new assets. Your rules transform assets in a truth-preserving way. That is, you take what you've got and you turn it into something new, and that new thing is still guaranteed to be true, assuming the truth of the first thing. So that's how you transform what you've got into something new, hopefully getting you to where you're trying to go. So these are the only 4 rules that I've presented you so far. So far, our box of rules are very, very simple. We've got modus ponens, modus tollens, double negation, and repetition. Repetition will become useful today, but really this is it. This is all you've got. It's not a lot, frankly. As we add new connectives, there will be new rules associated with them, but these are the connectives we've got so far. These are the only things that you can do. These are the only things that you can use to transform your assets into new assets and hopefully into the conclusion. Now, I didn't force you to do the parsing questions, but nonetheless, parsing is incredibly important for the rest of the course, and here's why. So here's how that parsing stuff that I introduced last week relates to these rules. These rules apply only ever to the main connective of the sentence. The only thing you can apply a rule to is the main connective of a sentence. That means that you need to be able to identify the main connective of the sentence, or you're going to misapply the rules and you're going to get it wrong. Okay? So that's why you need to know parsing. Parsing is the ability to look at a big complicated set of formula and figure out what the main connective is. Okay. So here's an example of doing it wrong. This is what you do not want to be doing. This is the situation you do not want to be in. So we've got if P, then if Q, then R, and you think, and you've got Q, and you think, I know what I can do here. I've got if Q, then R, part of that sentence, so I can apply modus ponens and get R. Great. But that's wrong, because that main connective of that sentence is if P, then this conditional. And you can only apply modus ponens to the main conditional. Here's a version of this in natural language showing you why this is wrong. So here's natural language versions of these 2 premises and the conclusion. If I'm feeling optimistic, then if it's sunny, then I'm happy. Right? A series of conditionals. If I'm feeling optimistic, comma, then if it's sunny, then I'm happy. It's sunny, therefore I'm happy. So if I'm in a depressed and pessimistic mood, it's still true that if I'm feeling optimistic, then it's sunny, then I'm happy. Right? That first conditional is still true. And it could nonetheless be true that it's sunny, but I'm in a foul, grumpy mood. I didn't sleep. My cat woke me up at 6 a.m. So it's sunny, but nonetheless I'm not happy. So this argument is invalid, and the reason why it's invalid is because what I've done is tried to apply modus ponens to part of the sentence rather than the main connective of the sentence. This sounds easy, but I guarantee there will be some of you making these mistakes by the end of the course, because you're not rigorously, carefully trying to identify the main connective and only applying these rules to the main connective. Here's something that you are allowed to do. Here's this going right. So you are allowed to infer, if you've got if P, then if Q, then R. If you've got P, then you're allowed to infer if Q, then R. So I've written the rules, and the Terry text, the textbook for this course, writes the rules as these box circle things. So the thing to keep in mind is that those the contents of those boxes and the contents of those circles are not necessarily atomics. They can be big complicated things. And if you have one big complicated thing, then another big complicated thing, and you have the first thing, then you get the second big complicated thing. But you can only do it to the main connective. You can't delve into the parts of the sentence and use the rules within. Okay? Hopefully that natural language example gives you a little flavor for why. But that's the general rule, even if it looks to you like it would make sense to do so. So I gave you an example where it didn't make sense in a natural, normal reasoning context. Even in cases where it looks like, oh, that's a reasonable move to make, nonetheless, you're not allowed to do this, right? You're only allowed to apply these rules to the main connective of the sentence. Okay. Here's another one that we're not going to accept. This is modus tollens. What I've done is assumed the double negation. I've assumed the double negation. And it's not hard to get not R from R, of course. You apply one rule, it's one step inference, it's trivial. Nonetheless, this is going to be wrong because we haven't done that double negation. Okay. So one way of understanding why this makes sense as a convention is that the rule is the thing on the right. The rule says you have to have the negation of whatever the conditional is. So negation of whatever that complex consequent of the conditional is, then you get the negation of the first part, right? Well, R is not the negation of the consequent of that. It's not. It's logically equivalent. You can, by the application of the rules, transform it into something that is the negation of that consequent, but it is not already the negation of the consequent. So we're going to be picky about this. Okay. So something that so this is the right one. This is what's a reasonable inference to make. Yeah? If you have the double negated version of it, that's the negation of the consequent, and therefore you can apply the rule on the right, modus tollens, to get the negation of the antecedent. Here's something that you're allowed to do, just by way of introducing you to some more features of the derivations. You can include more than one rule in a line. This is just to, if you want to make your derivations a little more compact, you can do this. The order of input is always the following. Input rule. So we've only got one rule with one input, that is double negation. But you say the thing you want to double negate, and then you say space dn for double negation. For any of our rules that require two inputs, so modus ponens and modus tollens both require two inputs, you say this thing and that thing modus ponens. So the two inputs come first, modus ponens comes second. Now, the reason why I'm talking about this in the context of compressed derivations is that you can sometimes have a complex input. And that's OK, too. So here's one where I've done just one thing at a time. So I have not, this is an uncompressed derivation. Suppose we've got the following three things as premises. We want to show not R. I could say premise 3 double negation, and then use line 2, where I got that as an asset, as an input to premise 2 modus tollens. Right? So modus tollens has these two inputs. I'm using a line that I've derived as one of my inputs. So that's how I showed you last time. That's a kind of normal case. You can compress it a little bit. So you can do the following. You can say premise 3 double negation, premise 2 modus tollens. So there, premise 3 double negation is an input, premise 2 is an input, and they both go into modus tollens. Okay? If you're nervous about this, if you don't feel that you're comfortable doing this, doing each line separately is completely fine. Okay? So if this worries you, do them on all separate lines. That's okay. You get no extra points for having the shortest derivation. Right? Okay. So you can compress your derivations. Okay. These are the rules. We briefly got into this last time, but it was too much at the time. So let's do this one more time about negations, double negations. So the thing that I just told you about double negations, how you have to have the exact match, right? You can't just use R and then you can't do this. This is the thing that I said you couldn't do. So I'm like, you gotta double negate it. You're only allowed to do this if you've double negated it. So we're going to be strict about that for all of the inputs to the rules. Now, you might reasonably ask yourself in this case, Do I have to write it as t, not t, or can I just write t? And we're going to say that for the outputs of rules, you can give yourself the version that you want. Okay? So for the inputs to rules, it has to be an exact match. If you don't give me the double negated version and you needed it, you got it wrong. For the outputs from rules, you can give yourself the version that you want. Okay? So a couple quick examples of this. The inputs have to match exactly. So if R then Q, you give me not Q, then and you have not Q, then you're allowed to do modus tollens on that, right? Because it's the negation of the consequent. The negation of that consequent is not Q. It's not Q. The thing on the right is not okay, right? Because you're giving me something that's not an exact match to the rule. The rule says the negation of this thing, whatever that thing is. If you don't match that exactly, you got it wrong. Okay? However, you are allowed to do the following. You're allowed to choose the output that you want. Either of these are going to be marked as correct. You got, if not P, then T, and you got not T. You can modus tollens that. And one valid thing to infer from that is not P. Another valid thing to infer from that, we're going to say, is just P. This will come up for, this is true for modus tollens. This will come up for several other rules that we're going to deal with this semester. So there's going to be a bunch of rules where the output could be one or the other thing. And I'm going to say for any of those rules, this is what we'll say. Inputs match exactly, outputs the way you want them. Okay? With the caveat that this only applies to the major connective. You only get it the way you want it for the major connective of the sentence. So this is not okay. The thing on the right, you're giving yourself the double negated version of R, but that's not the major connective of the sentence. So it's only when the whole thing is a double negation as output that you can give yourself the unnegated version. You can't go inside the sentence and manipulate those parts. Okay? Any questions about this? I'll remind you of this as we go along. Like we'll go over this several times. And if this is, again, if this is obscure to you, why I'm saying all this, it's probably because we haven't done the practical version. Like we have to actually enact these skills for these to be meaningful to you in a deep way. So, okay, let's move on. So, back to the strategy stuff. Back to how should you think about what you're doing in a derivation? How should you deal with your derivations? When you're looking at your premises, the thing you're trying to spot are places where you can apply the rules. This will become so natural and intuitive to you as you do the semester. So what you're looking for are opportunities to apply a rule. Anytime you apply a rule, you transformed what you got into something else, and that something else might be useful to you to get to the goal. So you're hunting for places to apply the rules that you've got. And at the exact same time, or maybe flipping between these two perspectives, what you want to do is be looking at the conclusion and asking yourself, how do I get there? What do I do to get to my conclusion? So let me show you this. Let me show you this as an example. Okay. So we've got this thing. Now, this is a fairly simple derivation. And that means that we would actually be able to solve this by going basically one direction or the other. So let's try just doing the forward-looking. So there's a forward-looking perspective on your derivation, and there's a backwards looking perspective on your derivations. You can start by just asking yourself, and it's often in a complicated derivation, it's often going to be the case that you have no idea when you just first look at it how you're going to get the conclusion. So it's often a good strategy just look at what you've got, what assets have I got available to me, and what can I do with them. So let's try that. So let's look at these things and say, okay, what have I got and what can I do with them? We got premise 1, we got premise 2, we got premise 3. Okay. Sorry, I'll try to remember to write PR because that's the way Logic 2010 wants it. Okay. So just looking at this in terms of what we've got, well, I've got Q and I've got this thing that if I double negate Q, that's the negation of this. So I can use Q and this to get something. So I can go like this. I'm going to use Q and that'll interact with this somehow. Good. Okay, so what did that produce for me? That'll produce for me the double negated version of P, which is equivalent to P. And then, okay, if I've got P, then I can use it over here, right? I can do modus ponens on this thing. Having P, I can get this thing. So cool. I can go here. And then that'll give me this thing, this conditional. And of course, I've got Q. I still got Q as a resource, so I can use Q to get me not R. Not R is the thing I wanted in the first place, so I'm done. Okay, so what I just sort of walked through there was looking at this derivation not as how am I going to get to the goal, it's just in terms of what have I got and what can I do with it. And we just kind of stumbled through the derivation asking ourselves, what have I got? What can I do with it? And then doing those things, and each step led us to the next step where eventually we stumbled on the conclusion. There's another perspective. So that works fine in super simple derivations like this. Like these are amongst the simplest derivations we'll do the whole semester. In simple derivations like this, that sometimes works. You can just forget about where you're trying to get and just see what you've got. Not a great life strategy. You shouldn't just like ignore your goals in life and just, well, here's what I've got. I guess that's what I'll do now. You should actually picture the end, right? You should picture where you're trying to get in your life and in your derivations. And it's very often helpful to do this backwards looking strategy as well. So suppose we start from where we're trying to get. So here's what you do. You say, okay, the thing I'm trying to get is not R. Okay, where does not R show up in my resources, right? It's not just going to come out of nowhere. It's going to come from somewhere. So not R shows up only in one place in these resources. Okay, so what do I need to get not R? Well, I need Q. Okay. Well, actually, if I'm going to get R, not R from Q, what I actually need is this whole conditional, which sort of means what I need is P. Okay. So now what I need to get not R, I need to get this whole conditional. To get this whole conditional, what I need is P. Okay. Now I look, where's P? Where does P show up in what I've got available? Well, P shows up here. Well, it's not P, but it's P still, right? It's a version of P that maybe I can work with. Okay, so how do I get this not P? Well, one way of getting it is by getting the negation of this thing. So if only I had the negation of this thing, I could get not P, or I could get not P, which is to say I could get P, and therefore I could get to my goal. Great, so how do I get the negation of this thing? Well, I would get it from here. So we just did the exact same derivation backwards and forwards. Do you see? We started from this time, the second time through, we started from where am I trying to get? And I just worked backwards from my goal. Okay. Again, in this fairly simple derivation, like I know it's not, I'm sorry to keep calling it simple, but compared to what you'll do by the end of the semester, this is quite simple. You can just adopt one strategy and stick with it, and it gets you to the end. When we do more complex derivations, what you're going to have to do is be able to flip back and forth. You might start by looking at what you got and maybe unlocking some resources for you, and then you'll have to say, okay, well, that's all the obvious stuff that I can see. What do I do now? And you'll have this sort of lost and lonely, confused feeling. And when you start having that feeling, it's time to flip perspectives and say, okay, where was I trying to go again? What was my goal here? And then you can start looking at it from the backwards looking perspective, and maybe that gets you a few steps. You could take a few steps backwards and say, okay, trying to get here, well, if I want to get there, I need this, and then I need this. Oh, now I see from the forward looking perspective where I want to go. And you can kind of like crunch your way through the derivation forwards and backwards. Let's just quickly do this derivation so that it's not, so that it's fairly straightforward. So we're going to show not R. Okay, so what do? We want to say premise 3 here, premise 1, 2, 3. I'm going to double negate it to get not Q. And then we're going to use line 2 and premise 2. Modus tollens. So not Q is the negation of this thing, which gives us, I'm just going to give myself P because I just said we're allowed to do that. We're allowed to choose the type of outputs that we like. Cool. So now on line 3, I have the antecedent of this thing. So line 3, premise 1, modus ponens gives me if Q, then not R. And if I've got if Q, then not R, well, I've got Q, so that was premise 3. And line 4, modus ponens, gives me not R. And that means that on line 5, I did a direct derivation. Box and cancel. And today is the day where I'll explain why I do this thing where I cross out the show line and draw a box around it. Okay, any questions so far? Good. Okay. So that was just a quick primer on derivation strategy. We'll have a lot more to say about derivation strategy as we go through the course because there will be more parts of strategy you'll need to learn. But I want to just lay this out right at the beginning because it's fundamental. This is fundamental to how you're going to approach all of your derivations. You're going to have to, typically, you're going to start out by writing a show line. No, not typically. Every single time, you're going to start out by writing the show line for the conclusion. You're going to make some moves which are fairly automatic. We'll talk about which moves are moves that are just, you just always do them because they can never let you down. So you'll do some automatic moves. You'll probably do some stuff of like, oh, I can see immediately that I could do this. So you'll start by adopting the forward-looking strategy, make some of the obvious moves, and then you'll probably have to switch to the backwards-looking strategy, asking yourself, okay, now that I've done the obvious stuff, now what should I be trying to get to? And that backwards-looking strategy will help show you it'll highlight for you where you want to go. And by looking at where you want to go, you can then switch back to the forward-looking strategy and say, okay, that's my new goal. Now, how do I get there from where I've got? And it's really just a back and forth between these two perspectives that you're going to have to do for most of these derivations. Sometimes you can just dumbly grind your way through it. That is, you can just sort of mechanically say, here's a move, there's a move, here's another move. I'm making moves. Hooray, I got to the end. And you just sort of surprise yourself by having solved it. That'll happen some of the time, but not less and less as the course progresses, basically. I hope that the exercises for last week were a little bit like that. You just kind of tried stuff, and then hooray, you got to the end, and then it was over, and that was good. So hopefully that's the level we start at, and as we progress, you're going to more and more have to think about, you know, okay, where am I? Where was I trying to get? Okay. So enough of that. Okay. So we'll start introducing right now conditional and indirect derivations. These are going to complicate our derivation system considerably. These are going to be features of all of the derivations you're going to do basically from here on out. So I told you that there was going to be a reason why you do this dd thing at the end of some derivations. That's a direct derivation. The contrast to direct derivations are indirect derivations or conditional derivations. So direct derivations basically just go straight from premises to conclusion. Now, that's not always going to work. So here's a conditional derivation. So here's a conditional derivation that you really can't do with a direct derivation. If it rains, the picnic will be canceled. If the picnic's canceled, then I get to eat all these sandwiches. Therefore, if it rains, I get to eat all these sandwiches. Great. Now, let's symbolize this. P is it rains. R is it rains. P is the picnic is canceled. And S is I get to eat all these sandwiches. Okay. Now let's try to derive this. Let's do this as a derivation. Here's our derivation. Okay. So always, 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 we're going to start with a show line. Line 1, I'm going to show if R, then S. Great. Now what? It's nothing. You can't do anything. There's nothing to modus ponens. There's nothing to modus tollens. You can repeat things all you want. You could double negate some of this stuff, but that's not going to get you anywhere, I promise. So far with the tools that we've introduced, you are utterly, utterly stuck in this derivation. But it looks like it should be derivable, right? This looks like the kind of thing that you should be able to derive. Okay, so we need to introduce something new, and what we're going to introduce is called a conditional derivation. When you want to show a conditional, what you do is the following. You start a conditional derivation. So what does a conditional say? Stop for a second and think. What does a conditional say? It says, if this first thing is true, this second thing has to be true. So if you want to show that a conditional is true, it's legitimate to assume that the first thing is true. And then if you can show by assuming that the first thing is true that the second thing follows, then you've shown that the conditional is true. You might ask yourself, but what if the first thing is not true? What if it turns out as false? Why is that not something we should worry about? Was that? Sorry. It's not dealing with true and false. It is dealing with true and false. Okay, so the answer is so consider the truth table for the conditional. Consider the truth table for the conditional. Recall what the conditional says. Say R, S, and then R, then S. Okay. True, true, false, false. True, false, true, false. Okay. So if R is true and S is true, then this whole conditional is true. If R is true and S is false, then the conditional is false. So if you want to show that this is true, the worst thing that could happen is if you assume R is true and S turns out to be false, right? That would make this conditional false. But if the antecedent is false, then the whole thing comes out as automatically true, right? So we don't care about the case where the antecedent is false. That's why it's legitimate to, if you're trying to show that the conditional is true, it's legitimate to assume that the antecedent is true. So that's the move we're going to make in this derivation. We're going to say R, and we're going to assume for conditional derivation. Okay? And now I'm going to write myself a second show line to show S. Okay. So assuming that R is true, can I now demonstrate that S is true? Giving myself R. And so recall we talked about your assets, what you've got. Well, now line 2 is something that you've got, something that you can work with. It's an asset that's available to you to do stuff with. Why is that an asset? How do we know that R is true? Well, what we know is that if we assume R and are able to show S, then that conditional is true. And that's what we're trying to establish here. Okay, so given that we've got R to work with, we can make some moves now. We are unstuck. We can say line 2, premise 1, modus ponens, giving us P. By the way, this is it's helpful if you indent after show lines so that you remember which derivation you're in, which subderivation. Okay, now we've got P, so we can say line 4 and premise 2, modus ponens again. And then we get S. And look, that's the thing locally within this subderivation. So we're calling this, when you start a new show line, so you got a show line for the whole thing, and then you start a new show line, that's what's called being in a subderivation. So it's a derivation within a derivation. So on line 5, I did a direct derivation for the thing that I was trying to show. Trying to show S, I showed S, great. I directly derived that. Okay. Now, what I've done is I've shown S on the basis of assuming R. So on the assumption that R is true, we've shown in a truth-preserving manner that S must be true as well, meaning that on line 3, we did what's called a conditional derivation, CD. And now we can box and cancel this thing. Right? Okay. So this is our second derivation type. Our second derivation type, conditional derivations. If you're trying to show a conditional, generally speaking, this is the way to do it. You start a conditional derivation. Couple of notes here. So the indentation thing, when you start writing things a little bit over, that's so that these boxes are all nicely not overlapping. If I hadn't done that, if I'd made these boxes, so I did this box all the way to here, and then I did this box all the way to here. Now I just can't read what's going on, which is annoying for the people trying to mark your papers fairly, right? So that's why we do this indentation thing. Subderivations get boxed like this. The other thing to note, and this is why we do this, okay, so this is crucially important. So if you've been drifting for a little while, now is a good time to snap back in. Okay, once you've, the action of boxing and canceling does the following. It turns this line from something that you can't use. So you're not allowed to use a show line until you've canceled it. Until you've shown S. So you can't look, this line 3 here says, I would like to show S. And look, I didn't offer any justification for that. Right? I didn't justify why I wanted to show S. You don't need to justify a show line. A show line is a goal that you're setting for yourself. It's not a thing that you claim to have shown already. It's, I would like to show this thing. Okay. Once you've finished the subderivation, you cancel the show part. You cross out show, and now line 3 is available. That is, you can use line 3 to do stuff. So if I had more deriving to do down here, now you can use line 3. What you can't use are the contents of this subderivation. So drawing this box around it is like saying, okay, that subderivation is over, and you're no longer allowed to use the contents of it. And exactly why will become clear when we do indirect derivations. But I think you can see it, actually intuitively, you can probably see it already, because what we did for this conditional derivation was to say, look, let's assume that R is true and see if we can derive S. Well, does that mean that R is true? No. No. You didn't magically spirit out of the air the fact that R is true, right? You assumed it and tried to show S because that would show that the conditional is true. You didn't show that R is true in reality. You showed that on the assumption that R is true, S will follow. So that means that you can get stuff that you wouldn't actually be able to get outside of this assumption that you've made for yourself, right? So it's not legitimate to now say, well, I know that it's raining. Based on this derivation, do you know that it's raining? No, but you know that if it's raining, you get to eat the sandwiches. So that's why we box, so you cancel the show line, say we're not trying to show S anymore, we showed it. Now we know S. But we box off the subderivation to remind ourselves that these are no longer available lines. These are not assets anymore. Before you box them, they were assets that you could use to do things. Once you've boxed them off, these are no longer assets for you. It's a little closed universe. You're not allowed to dig into it anymore. But what you've got is S. And then on the basis of S, we do so now I can cite line 3, right? So I can cite line 3 because it's a canceled show line. No longer trying to show S, I've got S as a resource, as an asset. So now I'm allowed to write line 3. So line 3, conditional derivation. Cancel and box the whole thing. Which is like saying, look, these are no longer things that I think are true. What I do think is true, however, is if R then S, which is the thing we're trying to get to all along. Okay? Okay, that's conditional derivation. We're going to use this a lot. And that's also our first ever subderivation, a derivation within a derivation. The mechanics of this are going to be not that tricky, but nonetheless something that you'll have to kind of work with a fair bit to get intuitively. So to get this as an intuitive skill, it will be some work. Okay. Actually, questions about this before we move on? Yeah.
At the very beginning, as for the second line, do we write the assume first or do we write the R first? Because what if we want to get the second premise first instead of the first?
Well, so as far as us reading your tests, I don't know which one you wrote first.
Okay.
You're not trying to get either of the premises, though. The question is, what if I'm trying to get the second premise rather than the first? You have premises. You try to get the conclusion. Yeah?
Yeah, because in this case, the premise 1 and premise 2 is in the correct order. But what if they are in the wrong order? So you want the second premise first to get the first premise.
Sorry, which lines are you asking about?
Second line.
Second line. On the second line, I'm assuming the antecedent of the conclusion. not either of the premises. Do you see what I mean?
Oh, yeah.
Yeah, so I'm not assuming that either of the antecedent of either of the premises are true. I'm assuming the antecedent of the conclusion is true. Good. Other questions? Yeah?
Is line 3 optional? Like, could we have done this without saying show S?
So, good question, a really good question. It is optional. That is, not writing that second show line doesn't make it wrong. And you'll see if you look at the textbook, they sometimes don't write it. So it's not incorrect. However, it's never a bad move. So I'm going to recommend that you always do this because that show line can be useful to you in ways that I haven't demonstrated yet. But when we get to indirect derivations, you'll see that show lines often give you options that you didn't have before. So as a matter of strategy, and anytime I'm writing a derivation, I always write the show line for the consequent. But you'll see in the textbook they don't always write that. They don't always write that because they know how the derivation's going to go, and they know they don't need it. But you won't know how the derivation's always going to go. You won't know whether you need it. So as a matter of the rules of the course, line 3 is optional. And it won't be marked incorrect if you do not include it. In terms of whether it's a good idea to write line 3, it is always a good idea to write line 3. It never harms you, and it can help you in a variety of situations. So that's why I would recommend, as a matter of how you do derivations, do write those show lines. But if you don't, that's okay. Okay. Any other questions? Okay. Let's take a break, come back in 10 minutes, and we'll do indirect derivations. Right, so that was conditional derivations. We just finished that, and exactly as I was saying just before the break, no, you do not always have to write the show line for the consequent. Again, you'll see this if you're reading the textbook, you'll see some places where they don't write the show line for the consequent. But you should, as a matter of good practice, write the show line for the consequent. Why is that, you ask? Well, let me show you. The reason why I'm going to show you this, the reason why it's a good idea is because you can use a show line to start what's called an indirect derivation. So indirect derivation is our third type of derivation that we're going to introduce before like this first test. Sometimes you can't get directly to the conclusion. Instead, we assume the opposite of what we want to prove and derive a contradiction. That's an indirect derivation. So if you can assume the opposite of what you want to prove and end up in a contradiction, then you've shown that that thing that you wanted to show is true. In our system, there's only true or false. There's nothing in between. There's nothing other than true or false. So if something's not true, it's false. And if something's not false, it's true. So if you assume the opposite of what you're trying to show, right, and end up with something that can't possibly be true, a contradiction cannot possibly be true, then you've shown that the assumption that you started with, the thing you're showing is false, must itself be false, and therefore the thing that you're trying to show is true. Okay. I don't know if there's any way to say this in a non-convoluted way, but there's the basic principle. So a contradiction is automatically false, always automatically false, at least in our system. There are systems of logic that accept contradictions, by the way. There are systems of logic, for example, where something can be true or false, or neither true nor false, or both true and false. Be grateful that we're not doing that in this class. So anything that's not true is false. So if you assume the opposite of what you want, show that it leads to contradiction. The thing that you wanted to show is guaranteed to be true. And that's all we care about. So immediately after a show line, you can assume the negation of that show line for the purpose of indirect derivation. The rule is assume ID, and that has to be directly after a show line. You're not allowed to do this just at random in the middle of a derivation. It's always immediately after the show line. Okay? So kind of house rules. If you want to do a conditional derivation, write the show line, you assume for conditional derivation and write the second show line. If you want to do an assume ID, you have to do it immediately after the show line. So let's do an example. We're going to do, okay. Right. Okay, as always, we're going to start all of our derivations with a show line. Show, this case, it's not the case that if v, then x, then y. Okay. Now, the thing to do here is not to start an assume ID, because the thing that we're trying to show here is a conditional. If you're trying to show a conditional, it's almost always, with only a very few very weird exceptions, going to be to start a conditional derivation. So I'm going to assume not v. I'm going to say assume for conditional derivation, just like we saw last time. And now we want to show if x, then y. Okay. Now the thing that we want to show is, again, a conditional. So the thing to do is, again, start a conditional derivation. We're going to assume x, assume for conditional derivation, and I want to show y. Okay. Now the thing we want to show is not a conditional, so we're just going to start a derivation. However, the thing that we're going to show here is in fact hard to show just going straight, right? So as a kind of general rule in derivations from here on out, if the thing that you're trying to show is not a conditional, it's good to start an indirect derivation. So what we're going to do is say not y. We're going to assume that for indirect derivation. Okay. Now that was a mildly complex setup, but we've got some, by doing this setup, now we've got some stuff that we can work with. So for example, okay, when you're doing these derivations, you set up your show line. So that's the first thing. And you just say, I'm trying to show a conditional. Okay, I'm going to start a conditional derivation. I'm trying to show another conditional. Okay, I'm going to start a conditional derivation. I'm not trying to show a conditional. Okay, I'm going to start an indirect derivation. Okay, so this is just setting up the show lines. Now, we're going to survey our available lines and ask ourselves if there's anything that we can do with these things. Right? So we start with a forward-looking strategy. Start with the forward-looking strategy and say, what have I got and what can I do with it? So what have you got? You've always got your premises, assuming there are premises. So you got premise 1, premise 2. So those are assets that you've got to work with. And you've also got these lines, line 2, line 4, and line 6. Those are all assets that you have to work with here. Okay? Things that are definitely not assets that you get to work with at this point are the show lines. Line 1, line 3, and line 5 are not things that you've demonstrated. These are goals that you've set for yourself. Okay. Now what? Now what do we do? I legitimately don't remember what to do. Okay. Thank you. Thank you. So, this kind person has noticed that there's something that we can do here. We have a rule that we can apply. We can say, on line 2, we have the antecedent of premise 2. So, we say 2, premise 2, modus ponens. We get t. Great. Okay, this time I'm not lost. Whew. So T is the antecedent of premise 1. Fantastic. So if we say we can say premise 1, line 7, modus ponens, we get if x, then y. Okay. And line 4 is still available, meaning that we can say line 4, line 8, modus ponens, to get ourselves y. Okay. Now we're really getting somewhere. Now we've got something good, because on line 6 and line 9, we've got y and not y. Those definitely can't both be true, right? Because the not just says the opposite. So line y, sorry, not y and y definitely cannot be true at the same time, meaning that we can close off this subderivation. So we've shown y by assuming that not y is true and deriving a contradiction. Notice that we've also shown y. We also ended up with y. So you can close this subderivation off in two different ways. You can say line 6, line 9, ID. And that's enough for me to say that we're done. Let's go with that for now. There's one more. You could just say line 9 direct derivation, but let's go with that. Okay. Okay, so now we've shown y by indirect derivation, by assuming the opposite of what we were trying to show and deriving a contradiction. We've shown y. Okay, so what are we trying to do again? We were trying to show y. Why do we want y? Because we were trying to show that if you assume x, you can get y, right? To show that this is true. So that means that on line 5, we've done a conditional derivation. We can say we've shown if x, then y. And why were we trying to show if x, then y? Well, that was part of an even bigger conditional derivation, trying to show that this whole thing was true. So we started saying, look, let's assume not v is true and see if we can get this thing. Okay, let's assume x is true and see if we can get this thing. Okay, let's assume that that's false and see if we can get a contradiction. We got our contradiction. So we showed that this thing is true. So we showed that on the assumption that this whole thing is true. So we can say on line 3, say it's on the line that you wrote the show line. You cite, once you've canceled the show line, you have this as an asset. You can say on line 3, I've shown that if x, then y. Therefore, on line 3, I did a conditional derivation. Ta-da. So that was our first, what's called mixed derivation. Sorry, that was not a mixed derivation. Sorry. That was the first time we've used both indirect and conditional. It's the first time we've had 3 embedded subderivations. Hopefully that's a good example of the indirect derivation. Yeah?
This is probably
Oh.
really dumb, but why do we have to keep going once we've proven a contradiction?
Right. It's not dumb. That's not dumb. Okay. So you might think once you've proven a contradiction, you're just done the whole proof. You're just, everybody go home, we're finished. But so what all you can do is close off the most recent subderivation. That's because we haven't shown that, so on line 6 and 9, we haven't shown that not y and y are both actually true. What we've shown is that on the assumption that x, we can derive this contradiction. Sorry, on the assumption that x and on the assumption that not y, we get this thing. So now we've shown y, but having canceled this, these lines, so that's what this box represents, is that these lines are no longer available. So we've created for ourselves a little sub-universe. We say, let's imagine that y is false and see what follows. Once we've shown the contradiction, we close off that little sub-universe and we forget about its contents. You have to say, okay, we're not allowed to use those lines anymore because those lines all are the result of imagining something is false when now you know it's actually true. So you cannot say, okay, I am a teacher. Suppose I'm not a teacher. That means I don't have to teach this class. Oh, I don't have to teach this class. I'm going home, right? That doesn't follow, right? You can't use things you've derived once you start an indirect derivation outside of the indirect derivation, right? And that's going to be really important going forward. You cannot just like reach out and assume things outside of your derivation. Okay. Okay. Any other questions? Sorry, I saw another hand over here, and yeah, hi.
Why is the indirect derivation necessary? Can't you just use the first two assumptions to prove why?
How would you do that?
If you assume not B, you get T. If you have T and you assume X, therefore Y.
Can't do this conclusion.
Sorry? Right.
You assume not B,
You assume not V, yeah.
so therefore you get T.
Yeah, so we got T.
You assume X. If you have T and X, you conclude Y.
But we've assumed X to try to show if X then Y. So you don't have if X then Y. You're trying to show if X then Y. Yeah, so this is not, if this was an available line before we finished this indirect derivation, then you could do that. But because before you finish this, you don't know if X then Y is true. That's why. Okay. Other questions? Yeah.
You're allowed to use the ones from the boxes above, right? In the subderivation, you're allowed to use assumptions that you made in like the level up derivation.
That's right. Yeah. But I made one mistake here. I should have used the repeat rule here. And I'll explain why shortly. Sorry. Oh, in here. Okay. I'll explain this shortly. But for our purposes, that's hopefully intuitive enough. Okay. Good? Okay. So we've introduced a fair bit this class, actually. There's a lot to take in right now. So we've introduced the idea of conditional derivations, of indirect derivations, and of subderivations. Just to get back to the overall strategy stuff for a second. Writing these show lines are what's called an automatic move. That is, you really don't have to think about them. If the thing you're trying to show is a conditional, you start a conditional derivation. If it's not a conditional, you start an indirect derivation. For now. There'll be one more wrinkle to this producing show lines like way later in the course, but for now, anytime you have a show line that's a conditional, you start a CD. Anytime you have something that's not a conditional, you start an ID. And this, by the way, is why it's always helpful to write the second show line after you say you're starting assume for CD. It's always helpful to have that second show line show the consequent, because that lets you start an indirect derivation. That's the advantage of having that strategically. So automatic moves. There's always going to be a bunch of automatic moves. And just to remind you of this idea of subderivations, it often becomes necessary to do mini derivations inside your derivation. And once the subderivation is complete, you box it off. The boxing off moment, so this concept of available lines is crucial. And people get confused about it in a chronic kind of way. By boxing off a subderivation, canceling its show line, you turn all of the contents of that subderivation into no longer available lines. Right? The box that you draw around it indicates to you that you're not allowed to use that stuff anymore. But by canceling the show line, you're making that show line now an asset that you have. So two things happen. The contents of the subderivation become no longer assets that you're allowed to use, but the show line becomes an asset. And you gotta keep those straight. Okay, so all of these things are possible. So here's a bunch of configurations of derivations that are possible. You can have, trying to show a conditional, you start a conditional derivation, you can have an indirect derivation inside of it. That's fine. I think that's what we just showed you. You can, if you're just trying to show something that's not a conditional, you start an indirect derivation, you might have to start a conditional derivation inside of it. That's also no big deal, okay? So these are both reasonable configurations. And, okay, I just talked to you about this, okay. So, should I go over once more? So I did just talk about, in response to a question, why you're not allowed to use the content of a subderivation anymore. Should I go over that one more time? You're all just kind of looking at me. Okay, I'll consider that well explained enough. Okay, here's the mistake I made in that derivation I showed you. I forgot to use the repeat rule. So before we started, the repeat rule was kind of useless. Before we started doing subderivations, it was in fact entirely useless because doing subderivations is the only time that it matters. But now, the repeat rule is going to be our license to bring something from outside of a derivation inside. And I'm going to require you to do this. So Logic 2010 only requires the repeat rule to be used to close off subderivations. So, but I'm going to, on your tests, require it all the time. Why am I doing that? I'm doing that because by the end of the course, many people remain confused about subderivations and seem to be unable to distinguish what's happening inside a subderivation from what's happening outside of it. So this is hopefully a pedagogical tool to help you keep crystal clear about what's going on in subderivations. So let me show you how I should have done this derivation. Okay. So this stuff is all fine. Okay. Okay, so got this far without making a mistake. Then I made a mistake. Because what I did was I took this thing, so I'm inside. So here's the thing that you need to get really clear on. What's inside your subderivation and what's outside. So right now on line 7, I'm inside the subderivation that I started on line 5. This is my little mini universe that I've created for myself by assuming something that I'm pretty sure is going to turn out to be false. Okay, so now if I want to bring anything inside the subderivation, I should do the following. So I want to use rule 2, or I want to use line 2 and premise 2. That means I have to say to repeat. And I could just do that. And that would give me this, not V. And then I can use not V with premise 2. So line 7, premise 2, modus ponens. You don't have to do those separately. You can just say to repeat, premise 2, modus ponens, and then get yourself T. Yeah? So that's, it's okay to, this is just me compressing 2 moves into 1 line. But I do want you to do this repeat rule thing. Yeah? So the repeat rule brings something from outside of the derivation, subderivation into that subderivation. Does that make it clear? I'm sorry, I can't hear you. Well, Yeah, but we're going to be real picky, basically. So again, Logic 2010 will require you to do this anytime you do a ID. So if you're using something from outside of the subderivation to generate a contradiction, then it will tell you that you're wrong for not using the repeat rule. It only strictly requires you to do it when you're closing off a subderivation. But again, I'm going to ask you to get into the habit of doing this every time you want to bring something from outside the subderivation inside the subderivation. Basically, these subderivations, again, they're like little mini universes that you've generated for yourself, where lots of false things are assumed to be true. That's the thing with doing, so a conditional derivation assumes something that you don't know is true, so it assumes more than you know. An indirect derivation assumes something that you're pretty sure is going to turn out to be false. So within a subderivation, you've got all kinds of unjustified and outright false things that you're working with. And that's why we want to keep these things strictly contained. You need to strictly contain what's going on inside your subderivation from outside. That's why I'm going to ask you to use the repeat rule every time you bring something from outside your subderivation in, and that's why when you finished a subderivation, you box it off so that you're not tempted to try to bring something from inside out. Okay? So that's the repeat rule. That's why we have the repeat rule. Are there further questions on this? Okay. Yeah, so this is just, if you've got x on line 3 and you wanted to bring it into this subderivation, you say 3, repeat. Okay. Okay. Here's something that starts off being very counterintuitive, but I promise actually makes sense. It's mixed derivations. So as it turns out, you can often start a derivation one way and end up finishing it a totally different way. And that actually works out fine in all cases, which seems like it shouldn't be true, but it is. So this is straight from the Parsing textbook. He says you may use DD, CD, and ID to complete a derivation by boxing and canceling whenever they apply, whether or not an assumption has been made, and regardless of the type of assumption, if any. This, by the way, is why I can't require you to say that second show line for the assumed CD, because it would violate this rule. So, but look what this lets you do. So if you want to show P, you can start an indirect derivation. And if you end up with P, you can just say direct derivation. Yeah? Why does that make sense? Why is that a reasonable thing to do? Because you kind of just saved yourself one line in this, right? You could exactly as well have said line 2, line 12, ID, right? And that would still give you the conclusion is true, right? So there's no possibility of going, if you start an indirect derivation and you end with a conditional derivation, there's no possibility of it going wrong on you. That's why it's okay in the system. That one I think is the most intuitive version, right? You assumed not P and you got P. It's just kind of a special case of the indirect derivation where you assumed the thing that you were trying to show in the first place. Or you assume you get the thing you were trying to show in the first place. So you start an indirect derivation, you end up with the thing that you were trying to show before you started the indirect derivation. You can write DD, and that's fine. It's called a mixed derivation because you started one way, you ended the other, but that's okay. Another thing that's okay is the following. You start a conditional derivation, but suppose for some reason you end up with the conditional you were trying to show rather than the consequent of the conditional. So usually you start a conditional derivation, you end up with the consequent, and then you say conditional derivation. But if you end up with the whole conditional, then you showed the conditional, right? You showed that the conditional is true, so you can just say, good, direct derivation, I'm done. Does that make sense? Yeah. Well, it does mean that you maybe didn't need it in the first place, but you probably didn't know that when you started. And it's even possible that the assumption of Q, so you might have used that Q to get that conditional somehow. So it could be that you didn't need it, it could be that you did need it, but nonetheless, if you get the conditional that was the original show line in your derivation, that's it, you're done. You showed the thing that you were trying to show and you're done. Okay. What if you don't start an indirect derivation, but nonetheless you derive a contradiction? This one's worth thinking about a little bit. It's a little less intuitive, but if you recall our definition of validity, it will make sense. Recall, these derivations are designed to demonstrate the validity of the argument. That is, if the premises are true, then the conclusion follows. Okay, so suppose you don't start an indirect derivation. You just start deriving things. Derive, and you end up with a contradiction. What does that mean? It means that there was a contradiction lurking in your premises somewhere. It might not have been obvious when you started, but by doing the derivation, you've drawn out some sense in which your premises were actually contradictory, which means they can't all be true, which means they can't all be true at the same time that the conclusion is false, which, if you recall, is our definition of validity. Right? So what have you done? By deriving a contradiction from the... Notice that the contradiction has nothing to do with P here. So you're trying to show P is true, and you derive two things that have nothing to do with P. It's Q and not Q. But nonetheless, what you showed is that your premises implicitly contain a contradiction. And if you've done that, then you've demonstrated for absolute sure that all the premises can't be true while the conclusion's false. Therefore, the argument is valid. It's valid in that weird, trivial way that we talked about. It's valid in the sense that it's impossible for the premises to be true while the conclusion's false because it's impossible for the premises to be true. But nonetheless, you've demonstrated validity. That's why this style of mixed derivation is perfectly okay. You don't start an indirect, but you ended it up with an indirect. Yeah?
Can you please say that again with like slightly different wording? Because I'm this close to understanding.
Okay. So, an argument is valid if the following two conditions can never be met at the same time. True premises, false conclusion. Those two can never be satisfied if the premises are contradictory. Therefore, it's valid. You're welcome. Okay. So, those were, I think, the trickiest cases of, mixed derivations. Do we get mixed derivations where, like, you start the derivation any way you want? Actually, you start the derivation in the way that I told you to. Do that. If it's a conditional, start a conditional derivation. If it's not, start an indirect derivation. Those are never moves that can make you go wrong. Those are only moves that can help you. Sometimes they'll turn out to be useless, like if you start an indirect derivation, but you derive the thing that you were trying to get on the show line. That indirect derivation might have been useless, but it didn't hurt you. It only opened up opportunities. So start your derivations that way and end them in any way you can. If you started an indirect, it's okay to end with direct. Start a conditional. If you start a conditional derivation and get a contradiction, you're still done, right? You still finish that derivation. So you start a conditional derivation, you derive a contradiction, you can say ID and box and cancel. You're done that subderivation. Okay, yeah?
So, if I'm understanding correctly, when you're telling us that we can do a mixed derivation
That's right.
So my question is, from what I understood, when we do a conditional derivation, we're entering like this other universe where we assume whatever is on the show line.
Yeah.
So if we haven't completed the process of showing whatever's on the show line, how can we take whatever is in the process of our subconditional to be true?
Right. So you're asking about the case where you start a conditional derivation and you end with an indirect derivation. That's really good. Okay, good. So I think I didn't do a slide for that, but we can mock it up. Just erase all this. Okay. So line 1, we want to show if P then Q. So we're going to assume P and then do a bunch of stuff. Now, suppose on line 11 we've got R, and on line 12 we've got not R. Okay, so why is it then valid to, on line 13, cite line 11 and 12 ID and close off this conditional derivation on that basis? So in this case, we've shown that on the assumption that P is true, a contradiction follows, right? But nonetheless, we've shown that this is a valid inference. So basically, it's essentially like the rules for a conditional being true are a lot like the rules for an argument being valid. That is, if you can show on the basis of assuming the antecedent a contradiction, so basically assuming P leads us into a contradiction, that means that P can never be true. And if P can never be true, then those two lines on the truth table both have the whole thing coming out as true. So it's like saying, if I am tall and not tall, then it is sunny. So if this contradiction is true, then the consequent follows. Just because of the weird way our conditional works, that conditional is guaranteed to be true because the antecedent is always false. That's why you can start a conditional derivation and end it with an indirect derivation. It's a good question. That's worth explaining. Good. Okay. Follow-ups on this? Does that make sense to you now? Yeah.
So can you only do this if you don't show P?
Well, you're not trying to show P.
Because if you do the CD,
Yeah.
then you show the P after, would you be able to do that?
Sorry, I'm not sure I understand the question.
Like when we do a conditional derivation and
Yep.
then we show the consequence,
Yeah.
would we be able to do the ID still?
Well, if you've shown, so here, if you've shown Q, then that's the end of this derivation. You just box and cancel it. So if you got the consequent, so you assumed the antecedent, if you get the consequent, then you're done. The ID is a way of closing off a conditional derivation without having shown the consequent. So if you got the consequent, there's no need to do the ID. You're just done in the normal way, what's called a uniform derivation. So 11 conditional derivation. Yeah? Good. Good. Okay. Any more questions about mixed derivations? You're asking good questions. This is good. Okay. I got one more topic we should talk about. So, using show lines. Again, the metaphor for life is helpful here. And it's important for you to understand what a show line is. Because people are constantly tempted to use show lines that they haven't canceled yet. Show line is not something that you know. It is not something you have available. It's a goal that you set for yourself. And just like in life, you do not have to justify your goals to anyone. You don't have to say why do I want to show that? You can just write, so at any point in any derivation, you can write any show line that you want. You just I want to show this. And often that's going to be helpful. Often that's going to be a reasonable thing to do because setting a new goal for yourself often liberates new resources for yourself. Again, exactly like life. Yeah? By setting a goal for yourself, that is writing a show line, you can then immediately assume ID, and then you have something new to work with. So if you get stuck, here's my general advice. If you get stuck, try to figure out a show line to write, because that will liberate new assets for you, all right? Via the use of the assume ID rule. Or via the use of, if you write a show line for a conditional, you get to assume the antecedent, and then you can make some more moves. So setting a new goal for yourself. Now, just like in life, many of the goals will be ones that are imposed on you by the situation that you find yourself in. So the first few show lines that you write are very often going to be just like, okay, the thing to be shown was sort of overall to be shown was imposed on you. Right? And maybe the next couple. So we saw one where I wrote 3 different show lines, and they were all automatic moves. They were all imposed on me. But that doesn't mean that they are all necessarily imposed on you. You can write your own show line at any point. And I don't recommend that you start just writing show lines willy-nilly, because a show line always has to be closed off before you can close off the whole derivation. You have to have reached the goals that you set for yourself. You have to close off the show lines. So you have to pick which show line to write very carefully, and it's kind of an art. Right? Deciding what show line to generate for yourself is a bit of an art. But nonetheless, you've done all the automatic moves. You did everything society imposed on you. You did the things that you were told you have to do. Now, for whatever reason, you're not getting to your overall goal of happiness or satisfaction or meaning or whatever. And you've done the forward-looking strategy. You say, okay, what have I got? All right, I don't know. I used all the resources that I have. You did the backwards-looking strategy. What's the overall thing? Happiness, all right. And you're still stuck. The thing to do in that situation is to generate a goal for yourself, a new goal for yourself. It's not just any goal, it's a goal that you're maybe possibly going to be able to accomplish. So you can't just like write it out of nowhere, but try to craft a goal for yourself. Try to craft a show line for yourself that will get you unstuck. So, and one that will be useful to you. I think maybe we'll do examples of this next time. I think we've probably used up enough of your brain juice today to justifiably call it a day. But we'll take up writing show lines next time. All right, thanks everyone.